everyone, this is Jessica Marie Emertito from BS Electronics 3A, and now in this video, we are going to talk about the flip-flop or the tsugols. Without further ado, let's start. So, in this juncture, what we need to know. So, what we need to know, the definition of the flip-flop, and also the EW simulation and summary. So, in this topic, definition of flip-flop, we are going to talk about the theory of the operation and describe the characteristics, and we are going to determine its characteristics, logic symbol, logic circuit, excitation, and table, and etc. So, first, T flip-flop is in the theory of operation. The T flip-flop is designed by passing the A and D gates output as input to the NOR gate of the SR flip-flop. The inputs of the A and D gates and the present output state Q and its complement Q are sent back to each other and A and D gate. The toggle input is passed to the A and D gate as input. So the characteristic, defining the characteristic of T flip-flop is that it can change its output state. You can change the output signal from one state on or off to the another state on or off or on, then the clock is set low. The output remains and it's whether the input signal is set high. So we are going to do the simulation, so we are going to know more further about the T flip-flop here. So in the logic circuit here, so a gated latch is useful component, but the output can change whenever an enable signal is high. It introduces a lack of precision and reliability into whatever digital interface built around the latch. It would be better if the latch would respond to input changes only at a specific moment in time. The trouble is, once we have implemented this functionality, the latch is no longer a latch, it's a flip-flop. So here, as you can see here, we are going to simulate that one, and we're going further to know in the simulation. Okay, so the pulse transition detector (PTD) converts a rising or falling edge into a short pulse. This pulse becomes an enable signal such that the latch is enabled only for the short period of time following the transition. The latch pulse PTD arrange is that we call a flip-flop. And since we are usually working with logic circuits that are governed by clock signals, the flip-flop's enabled signal is often referred to as simply the clock. So here is the graphical symbol of the T flip-flop. The transition table here, wherein Q times T plus 1, wherein 0. If the QT are both 0, then the Q plus T plus 1 is 0, or the input, or the output, I mean. If the input is 0, 1, then the output is 1, as well as 1, 0. And if 1, 1, it equals to 0. So if they're the same binary digits, 0, 0, 1, 1, the output will become 0. So here, T flip-flops are handy when you need to reduce the frequency of a clock signal. If you keep the T input a logic high and use the original clock signal as the flip-flop clock, the output will change state once per clock period. So, assuming that the flip-flop is not sensitive to both clock edges, thus the output clock will be half of the frequency of the input clock. If you know a clever use for a T flip-flop, let us know in the comments. We're going to know. So here, as you can see, when the T input is low, then the state of the T flip-flop is same as the presented state there. If T is equal to 0 and the present state is 0, then the next state is equal to 0. If T is 0 and present state is 1, then the next state is equal to 1. So when the T output is high and during the positive transition of the clock signal, the next state of the T flip-flop is the complement of the present state, right? Diba? If T is equal to present 0, then the next state is 1. If T and the present state is 1, then the next state will be 0. That's what I said here in the transition table. So this is the truth table and the excitation table of T flip-flop. As you can see, I have already explained this one. Here is also. So we are going to proceed into the simulation. So first, let me fix my camera. So this is my simulation. Okay. let's write the arrangement here. There we go. Here, as you can see in my simulation, we're in the T or toggle and the C clock is off, right? So let's try to off that one. So let's try to on. There we go. So you can see the Q and the Q bar is on latch, right? As you can see, if the toggle is off as well as the clock is also off, then the output Q and Q bar is latch. As you can see, nag-appear na siya. So let's try if the clock is on, right? And the T is off, what we're going to see. So yes, as you can see, the output Q and Q bar is also on latch. So now, let's try the other one. So let's try if the clock is on and the T is also on. So the clock here is already on now. Let's turn on T, the toggle. Let's start. Sing as the circuit is toggled on. So both are all of the nodes or the light is in the latch or it's been toggled. That's mean that the circuit is function. Okay. Now let's try. Let's try if the clock is off and the T is on. There we go. It's off. The T is on and the clock is off. So what will happen? Sige, naka-latch man. Also, the circuit is latch man. The Q and the Q bar is of the output is also in latch. So that's it. So let's have a further explanation on the summary. So the summary here. Okay. There we go. There we go. So yeah. Now for the summary, here is my summary. So the T flip-flop is designed by the passing the AND gate's output as input in the NOR gate of the SR flip-flop. The inputs of the AND gates represent outputs Q state Q, that's what I see in the simulation, and is complemented by Q bar are set back to each and AND gate. The toggle input is passed on the AND gate as an input. So the T in the T flip-flop means toggle. So that's all. This is Jessica Marie Amlartizo. This is ECE or Electronics Engineering 3A. And this is video number 11. ECE 27. And that's all. This is T flip-flop, which means T in that T flip-flop is toggle. That's all. Thank you.